So in chapter 13, we're going to be looking at what is called a one-way ANOVA. ANOVA stands for Analysis of Variance. And what the purpose of a one-way ANOVA is for is to make a comparison of three or more means. So you may remember back in chapter 11, we looked at like comparing two different proportions or two different means. So here, it's not just going to be two different means that we're comparing. We're going to be comparing three or more different means. So definition, an analysis of variance, or ANOVA, is an inferential method used to test the equality of three or more population means. So again, what that means is we're going to be checking to see, are these three or four or five or six or however many different population means equal to each other or not? So consider the hypothesis regarding three population means. Now, this is a case where there's three population means as opposed to 4, 5, or 6 or whatever. But if we had 4, 5, or 6 population means, it would be structured the same way. The null hypothesis will be that mu1 equals mu2 equals mu3. Again, if we have three population means. So again, the mean from population 1 equals the mean from population 2 equals the mean from population 3. That's the null hypothesis. The alternative hypothesis would be that at least one of the means is different from the others. So what does it mean for at least one of the means to be different from the others? Well, it might mean that none of them are equal to each other. So mu1 and mu2 and mu3 may all three be different things. Or it could be possible that like mu1 and mu2 are equal, but mu3 is different from those two. Or it could be possible that like mu1 and mu3 are equal, but mu2 is different. Or it could be that mu2 and mu3 are equal and mu1 is different. And again, if we had more than three means, then it would work the same way. There would just be more combinations of how things could be equal or not equal and so on. So figure A below shows the distribution of each population if the null hypothesis is true. So if you take a look at this figure here, if all of the means are equal, so if the null hypothesis is true and all the means are equal, then mu1 equals mu2 equals mu3, so all of those distributions are going to have the same shape, the same center at least. Figure B shows one example of what the distributions of the populations might look like if the alternative hypothesis is true. So if there's at least one that's different, we might end up with a graph like this. In this particular case, it would appear that all three of the means are different. So this would be one possible case. So like here's the population 1's distribution, here's population 2's distribution, here's population 3's distribution. And so they all look to be somewhat different in this kind of case. So again, this is one possibility if the alternative is true and the null hypothesis is false. Now caution, we do not test the null hypothesis mu1 equals mu2 equals mu3 by conducting three separate hypothesis tests, because the probability of making a type 1 error will be much higher than alpha. So one thought is that if I wanted to test whether these three means are equal, is I could just say, well, is mu1 equal to mu2? I could test that like we did in chapter 11. Is mu1 equal to mu3? And I could test that like we do in chapter 11. Is mu2 equal to mu3? I could test that like we did in chapter 11. But again, the reason why we don't do that is because the probability of making a type 1 error is higher than the level of significance would be, and that's the issue. So we use this ANOVA test instead. Analysis of variance, or ANOVA, involves a comparison of two estimates of the same population variance. The procedure used in this section is called a one-way ANOVA because only one factor distinguishes the various populations in the study. Now, requirements. The requirements to perform a one-way ANOVA, and there are 4 of them that we're going to concern ourselves with. 1, there must be k simple random samples one from each of K populations, or a randomized experiment with K treatments. So we have to have randomness. So it's the same sort of idea that we've had forever. We have to have randomness in the selection of the samples. So if we have 3 populations, we have 3 samples, one from each population. If we have 4 populations, we have 4 samples, one from each of the populations. 2, the K samples must be independent from each other. That is, the subjects in one group cannot be related in any way to the subjects in the second group. Again, we've seen this over and over with the different hypothesis tests and confidence intervals that we've been doing. So the individuals in sample 1 cannot be related to the individuals in sample 2 or sample 3 or sample 4. They have to all be independent from each other. 3, the populations must be normally distributed. So if we have small samples, we may have to perform a normal probability plot or a QQ plot in order to verify that the population is normal. We also generally don't want to have any outliers as well. If we have large samples of 30 or more, then we will assume by the central limit theorem that we have an underlying normal distribution. 4, the populations must have the same variance. That is, each treatment group has population variance of sigma square. So again, this is a requirement that all of the populations have to have the same variance. Now, the methods of a one-way ANOVA are robust, so small departures from the normality requirement will not significantly affect the results of the procedure. Also, the requirements of equal population variances does not have to be strictly followed, especially if the sample size for each treatment group is the same. So it is a good idea to design experiments where the sample sizes are approximately equal. So as a general rule, we want to have the 3 or 4 or 5 different samples. We want them to all be at least approximately the same size, if not exactly the same size. We wouldn't want to take one sample that has like 10 individuals and another sample that has 100 individuals. We want them to be relatively equal. And if that's the case, then we don't have to follow the requirement of equal population variances strictly. They still need to be relatively equal, but they don't have to be perfectly equal. So how are we going to go about verifying all of these requirements? Well, we can control whether our samples are selected randomly, and we can make sure that the samples are independent from each other. Also, we can verify whether the population that the data comes from is normal or not, or whether it probably is normal. Again, either we have to have a sample size of 30 or larger so that the central limit theorem applies, or we can construct a normal probability plot or a QQ plot in order to verify that the data most likely comes from a population that is normal. But how do we verify the requirement that the population variances are equal? Well, the one-way ANOVA procedure may be used if the largest sample standard deviation is no more than twice the smallest sample standard deviation. So if we find the standard deviations of all of our samples and figure out what's the smallest of those sample standard deviations and what is the largest of those sample standard deviations, as long as the largest is no more than double the smallest, we're good. That will satisfy the requirement that the population variances are equal. So example. So researchers Sharon Peterson and Madeline Sigmund Grant wanted to compare the overall nutrient intake of American children who exclusively use lean meats, mixed meats, and higher fat meats. The data below represent the daily consumption of calcium in milligrams for a random sample of 8 children in each category and are based on the results presented in their article, Impact of Adopting Lower Fat Food Choices on Nutrient Intake of American Children, which was published in Pediatrics, Volume 100, number 3. So I have 2 parts to this example, and I'm going to carry this example throughout the rest of this chapter. So question A, I want to state the null and alternative hypotheses for this study. And B, we want to verify that the requirements to perform one-way ANOVA are satisfied. So A, now we have 3 different populations, so we have samples from each of those populations. We have the population of children who consume only lean meats. We have the population of children who consume mixed meats, meaning like some lean meats and some higher fat meats, or something in between. And then we have a population of children who consume only higher fat meats. And so again, we have samples from each of those populations. And what these data values are, again, represent the calcium intake in milligrams. So one child had a calcium intake of 844.2 milligrams. Another one had a calcium intake of 745.0 milligrams, and so on. So in A, we want to determine our null and our alternative hypothesis. So our null hypothesis is going to be that the mean calcium intakes for all 3 populations are equal. So I'm going to denote that by mu sub L, that's for lean meats, equals mu sub M, that's for mixed meats, equals mu sub H, that's for higher fat meats. So I'm saying that the calcium intake on average for all 3 populations is the same. That's my null hypothesis. My alternative hypothesis is going to be that at least one mean is different. Now again, when I say at least one mean is different, what it could be is that it could be that we conclude that all 3 of them are different, so none of them are equal, or we might conclude that 2 of them are equal and 1 of them is different from the other 2. Question B. Verify that the requirements to perform one-way ANOVA are satisfied. So if I bring back in our conditions, our requirements, so there must be K simple random samples from the K populations or a randomized experiment with K treatments. Well, in this particular case, we have 3 populations, and so we have 3 samples that are randomly selected. So the data below represent the data consumption of calcium for a random sample of 8 children from each category. So these were randomly selected. So we do have randomness. 2, the K samples must be independent of each other. So now it doesn't specifically say that in the setup of this problem, but I think we can assume that the children, these 8 children who consume only lean meats, are not related in any way to the 8 children who consume only mixed meats or the 8 children who consume only higher fat meats. And the same, the mixed meats children are not related in any way to the higher fat meats children. So these 3 groups are independent from each other. So I think we meet that condition. So I'll just go ahead and say here, we have randomness. Check. We have independence. Check. I think we can, again, safely say that we have independence. 3, the populations must be normally distributed. Well, how am I going to verify that? Well, I can verify that by creating a normal probability plot or a QQ plot. So I am going to do that using StatCrunch. Here you can see my StatCrunch screen. And prior to starting this video, I have entered the lean meats, the mixed meats, and the higher fat meats data into my StatCrunch spreadsheet. And so I'm going to create a QQ plot for each of these three groups to verify that we have normal distributions. So I'm going to go to Graph, and I'm going to go to QQ plot, and I'm going to select all three of the groups: lean meats, mixed meats, higher fat meats. I want to calculate the correlation statistic because I'm going to compare that in just a minute to the critical value. And I want the normal quantiles to be on the y-axis. So if I say compute, the first graph that I have right here is for the lean meats data. And so I can see that that is somewhat linear. We have a correlation coefficient of 0.991. And I'm going to write that down on my paper, which I'll show you in just a second. So the correlation coefficient for the lean meats is 0.991. Now I'm going to move to the next graph here, and this is for the mixed meats. And so again, I can see that is somewhat linear, and we have a correlation statistic of 0.988. So I'm writing that down on my paper. And then for the third group, now if you look at this graph, that graph is a little less convincing that it is linear, but we do have a correlation statistic of 0.951, which is pretty close to 1. So I have just written down, this was the correlation statistic, again, for the lean meats. This was the correlation statistic for the mixed meats. This was the correlation statistic for the higher fat meats data. In all three cases, we have sample sizes of 8. So for each case, our sample size is 8. And so I'm going to bring in table 6 from the appendix of our book. And if we have a sample size of 8, the critical value for the correlation statistic to show that we have a normal distribution is 0.906. So our critical value is 0.906. So because all three of our correlation statistics are greater than 0.906, that indicates that all three populations probably come from distributions that are normal. In other words, these three different sets of data probably come from normal populations. So again, just to be clear, the correlation statistics for lean meats, 0.991, that's bigger than 0.906. So this lean meat data probably comes from a population that's normal. For mixed meats, the correlation statistics, 0.988, that's bigger than our critical value. So this mixed meat data probably comes from a normal population. And similarly, the correlation statistic for the higher fat meats, it's lower, but it's still 0.951. That's still bigger than 0.906. So this data probably comes from normal population. So that's our third condition that's met. And then our last condition, the populations must have the same variance. So the way I'm going to verify that is I'm going to find the standard deviation of all three samples, and I'm going to make sure that the largest of those standard deviations is no more than double the smallest. So here we are back in StatCrunch again. I'm going to move the normal probability plots out of the way here, and I'm going to do stat, summary stats, columns. And I'm going to select all three categories and say compute. And that's going to find a lot of summary statistics. Included in that are the standard deviations. So I'm going to write those down. So the sample standard deviation for the lean meats is 33.966 if I round to 3 places. The standard deviation for the mixed meats is 40.399 if I round to 3 places, and the standard deviation for the higher fat meats is 38.885. So of the three standard deviations, 33.966 is the smallest, 40.399 is the largest. And so because the largest standard deviation is not more than twice the smallest, we meet the condition of having equal variances. So again, I'm going to say our largest 40.399 is less than 2 times 33.966. So our largest standard deviation is less than double the smallest. So our populations have close enough to equal variances that we meet the condition. So all 4 conditions are met. So that's the first thing we have to do when we are going to conduct an ANOVA test. We have to make sure that the conditions for conducting the ANOVA test are met. If the conditions are not met, we can't do the ANOVA test.